It says for a class B amplifier with VCC equal to 25 volt, driving an 8 ohm load, determine DC power, maximum output power, maximum efficiency. Okay, so this is the given problem. Okay, it had come for 6 months. So solution, let us take. Okay. Now, if you look at the problem, they have simply mentioned that it's a class B power amplifier with VCC value of 25 volt and RL is equal to 8 ohm. But in class B, we have two types of power amplifier circuits, right? We have a transformer coupled class B push-pull power amplifier circuit, and we also have a transformer-less complementary symmetry power amplifier circuit. Since there is no information regarding the type of power amplifier circuit, the question comes something like which power amplifier circuit I need to consider. Okay. Now, if you go with the logic, you can make out that for a complementary symmetry class B power amplifier circuit, this much data is enough to go with the solution, right? On the other hand, if you go for a transformer coupled class B power amplifier circuit, you would be needing an additional information, something like the transformation ratio, the transformer details, etc., etc. Okay, so since there is no information of transformer, you can consider this particular circuit as a complementary symmetry class B power amplifier circuit. So in the solution, first statement would be the justification why you are considering complementary symmetry power amplifier circuit. So let me write it down. Okay, since there is no data about the transformer, the given circuit is considered as complementary symmetry class B power amplifier. Okay, so let us consider it as complementary symmetry class B power amplifier. Okay, all right. Now let us write down the given data. So VCC is given 25 volts. Then you have been given with the load detail 8 ohm. Okay, so two things are given. Now let us start finding out the unknowns, that is the DC power, maximum power output, and eta maximum. So first let us write DC power. DC. Okay, but you have to be a little futuristic in the sense, what is that in the end you are trying to find out? So you're trying to find out eta maximum. So to get eta maximum, you have to apply the condition for maximum efficiency, right? So you can write something like for eta maximum, okay, the condition is maximum voltage should be equal to the power supply voltage, right? Vm is equal to VCC. Okay, therefore you can find out the maximum value of current, load current. So Im is equal to Vm divided by R. Right? What is Vm? Vm is equal to VCC, right? So it is nothing but VCC by RL. So that is equal to VCC is 25 divided by 8. So that gives the current as 3.125 amperes. Okay, 3.125 amperes. So that's your IM. So once IM is known, you can find out the DC power. So DC power, PDC. Okay, PDC is equal to VCC into IDC, which is equal to VCC into IDC. IDC is 2 IM by pi, because the DC values of two collector currents are added to get IDC value, right? So that is 2 IM by pi. So what is VCC? VCC is 25 into 2 into IM. IM is 3.125 divided by pi. So that gives PDC as 49.73 watts. Okay, 49.73 watts. Okay, so that's your PDC. So you're done with the first part. Next, let us find out P naught max. Okay, so P naught max, pretty simple. What you can do is you have, first you write down P naught AC. Okay, so P naught AC is VM IM divided by 2. Okay, so you can write down, you can also write down the value of IM, but we want to find out the maximum value of power output, right? So let us convert this equation into kind of voltage way. So you can write it something like VM divided by 2, and IM can be written as VM by R, right? Or you can write, yeah, tell me.
So PDC is 49.37 or 49.73?
73, sorry. PDC is 49.73. I think 73. Okay, it is 49.736 watts. So 2-digit approximation is sufficient. Okay. So P naught AC is equal to, basically it is VM square divided by 2RL. Okay. Therefore, the maximum P naught AC max is, okay, for P naught AC maximum, what is the condition? VM should be equal to VCC, right? So P naught AC maximum is basically VCC square divided by 2RL. That is 25 square divided by 2 into 8. How much will get? $25 square. Will you get 39.06? So P naught AC is 39.06. Okay, so that's your maximum power output, and power output is always AC for class P power amplifier. So, and finally we have percentage efficiency, eta maximum. So eta maximum is P naught AC maximum divided by PDC. Okay, so P naught AC is 39.06 divided by PDC. PDC is 49.73. Okay, since you're talking about maximum efficiency, you should get this value very close to 78.5%. Okay, because theoretically we have already found. Okay, so that's your first problem. Clear? Second problem, let's consider. So the problem statement goes like this. A complementary symmetry push-pull amplifier is operated using VCC is equal to plus or minus 10 volt and deliver power to a load RL equal to 5 ohm. Calculate maximum power output. Second, power rating of transistors. Third one, DC input at maximum power output. Okay. So this is the problem statement. Okay. Now this problem was asked for 8 marks. Okay. So here they have clearly mentioned that it's a complementary symmetry push-pull amplifier, not transformer coupled push-pull amplifier. Okay. So and there's one more point to be noted that the VCC, they have also mentioned it as plus or minus 10 volt, but we can always take plus 10 volt because the other transistor is going to be the identical transistor, but works for negative voltage and current levels. All right, fine. So first let us look at the data. So VCC value is given and resistance value is given, and you have been asked to find out maximum power output. So power output is always AC. So let's start off. So let us write PAC maximum, okay, is equal to P out, because sometimes I may write it as just P out itself. Okay, so P out is nothing but the AC power delivered to the load. Okay, once again I want to write the expression. So PAC, first let me write, is equal to VM IM divided by 2. Okay, or you can also write it as VM square divided by 2 RL. Okay, so at maximum power condition, okay, VCC is equal to VM, right? So VM square needs to be replaced with VCC square. So it is VCC square divided by 2 RL. So you will get PAC maximum. Sorry, here. So PAC maximum is VCC square divided by 2. Okay, so therefore PAC maximum is equal to VCC. VCC is 10 square divided by 2 into RL. RL is 5 ohm, correct? Yeah, RL is 5. So it is basically 10 watts. So first part is calculated. Okay. Next we have power rating of the transistors. Okay. So in the previous class, I don't know whether you have gone through. Yeah, the power rating of the transistor is calculated on the basis of maximum power dissipation. So let me write power rating of the transistor is calculated on the basis of maximum power dissipation. Okay. In other words, PD maximum. Okay. So how do you find this PD maximum? You see, I can directly write an expression, but let me derive that particular expression, though I have done in the previous class. Once again, I'm going to do it. So how do you find PD maximum? First of all, you define PD. PD is nothing but the waste power or power dissipated in the device, okay, which has not taken part in energy conversion. So PD is equal to input minus output. Okay, that is the waste power. Or input is PDC and output is AC. Okay, so PD basically you will get it as PDC is VCC, okay, into IDC, right? IDC can be written as 2Im by pi, okay, minus PAC VM Im divided by 2, or this can also be written something like VCC into 2 by pi. Okay, in place of Im, let me write it as Vm by RL or RL dash, doesn't matter. If at all you were to refer RL onto the primary side. And this one, let me write it something like Vm. Im can be written as Vm by RL, so this becomes Vm square by 2RL. Okay, 2RL. Okay, so that is your PD. Okay, now expression for, then what you do is you differentiate PD with respect to Vm and equate it to 0. This step you can refer the class notes. Okay, so this condition basically gives, PD max. This is condition for PD max. Okay, so this condition will give you Vm is equal to 2 by pi VCC. Okay, so in order to find the maximum power dissipation, what you have to do is you have to substitute equation 2 in equation 1. So substitute equation 2 in equation 1 for PD maximum. So therefore, PD maximum is equal to VCC into 2 by pi into Vm. But what is Vm? Vm to be replaced with equation 2. Vm is 2 by pi into VCC. So it is 2 by pi into VCC divided by RL minus Vm square. What is Vm square? 4 by pi square, right? Into VCC square divided by 2RL. So Vm square is this entire term square. So 4 by pi square into VCC square divided by 2RL. Okay, so 2 goes 2 times in 4, and VCC you can multiply, and 2 by pi becomes 4 by pi square. So this basically you can write it like 4 by pi square, the first term I'm writing, 4 by pi square into VCC square divided by RL minus, this is 2 by pi square VCC square by RL. So basically you are subtracting the second term from the first term. So when you subtract, what do you get? you get PD maximum as 2 by pi square. You're subtracting, right? It is 2 times greater than the second term. So it is 2 pi square into VCC square divided by RL. So this is the condition for PD maximum. Okay. If I wanted, I could have directly written this formula, but I thought once again I will do it so that you will not end up in by hearting the formula. You can quickly derive this particular formula. So coming back to our problem, we can write PD maximum is equal to 2 by pi square, which is a constant, into VCC square, right? What is VCC? In the problem, VCC is given as 10. So that is 10 square by 5. Okay, let's see what answer it gives. Did anyone calculate? 2 by pi square, what answer it gives? .05 watt. So that's your maximum power dissipation. Okay, maximum power dissipation. So once the maximum power dissipation is known, you can find out power rating of the transistors. Okay. So therefore power rating for each transistor is equal to, how many transistors will you use for class B operation? 2. So it is PD max divided by 2. So that is so let me just write in short, rating per transistor. Okay, that's 2.02 watts. That means to say whatever transistor you are taking, that transistor should be able to withstand a power of 2.02 watt. So if you were to design the circuit, okay, if at all you assume a circuit designer's role, then you must ensure that your transistor rating is above this. Okay, so plus a 10% buffer you may have to take, okay, to safeguard the transistor. So that's the second part. Okay. Third part. In the third part, you were supposed to find PDC for maximum efficiency, I think. Yeah, PDC, that is DC input at maximum power output. Okay. So PDC for maximum power output. Okay. So pretty simple. Now, to find PDC, first let us write down the formula. That is VCC into IDC. IDC is 2 Im by 5. So what is this Im? So Im is basically Vm by RL, right? So Vm is 10, okay? Because let us take Vm is equal to VCC for maximum power output, okay? So it is 10 divided by 5. That is 2 amperes. So Im is 2 amperes. So therefore, PDC is equal to VCC. It is 10 into 2 into Im. Im is also 2 divided by pi. So you will get PDC as 12.7323 watts. Okay. So that's your DC output for maximum. Sorry, that's your DC input in order to get maximum output. Okay. So that completes problem number 2. Any doubts till now? Okay. All right. Third problem, let me take. So it says Class B push-pull amplifier operating with VCC equal to 25 volt provides a 22 volt peak signal. That means to say maximum value is 22 volts. Provides, let me repeat, provides a 22 volt peak signal to an 8 ohm load. To an 8 ohm load. And you have been asked to find peak load current second, DC current drawn by the supply. Third one, input power. Fourth one, output circuit efficiency, or in short, efficiency. And fifth one, power dissipation. Okay, so this problem had come for 10 marks. 10 marks. Okay, all are very important problems. Fine. So this is the given problem, which says that the power supply voltage is 25 volt and the circuit is giving a peak voltage of 22 volts. Okay, and the connected load is 8 ohm resistive load, and you are supposed to find out peak load current. Peak load current is nothing but the maximum load current, and followed by the DC current drawn by the supply, input power, efficiency, and then finally power dissipation. All right, fine. So let us solve this problem. Okay. So peak load current. So peak load current, first let us define peak load current. Let us take it as IM. So IM is equal to VM by RL, right? So what's VM? VM they have given 22, okay, divided by RL. RL is 8. So 22 by 8 is 2.75 amperes. Okay, so that's your peak load current. Second one, DC current drawn by the supply. So DC current drawn by the supply is IDC, and IDC is 2 IM by pi, right? IDC is 2 IM by pi. So therefore, IDC is equal to 2 into IM. In the previous step, we have calculated IM, so that's 2.75 divided by pi, right? So how much will you get? It's 1.75. So IM is IDC is 1.75 amperes. Okay. The third part, power input. So power input PI is equal to PDC, right? Power input is PDC. So PDC is VCC into IDC. So VCC is 25 into IDC is 1.75. So when you multiply, you will get it as 43.76 watts. Okay, in and around 43.76 watts. So that's your third part of the problem. Okay, fourth part, efficiency. Okay. So percentage efficiency is P0 AC divided by PDC. Okay, so to find efficiency, you need to find out P0 AC. What is P0 AC? P0 AC is VM square divided by 2RL. So that's 22 square divided by 2 into RL. RL is 8. So how much will you get? 30.25 watts you will get. All right. So you know now P naught AC. So it is 30.25 divided by 43.76, and that gives a conversion efficiency of 69.11%. Okay. So 69.115% is the conversion efficiency. Okay. So finally, we are left with the power dissipation. So power dissipation is defined as PD, and PD is PDC minus PAC. DC is 43.76 minus PAC is 30.25. So that gives a power difference of 13.51 watts. Okay. So therefore, PD per transistor is equal to 13.51 divided by 2. That's about 6.75 watts. Okay. So that completes problem number 3. Okay. So you can expect such problems in case of class B power amplifier operation. Okay. So today what I will do, I will give you 2-3 numericals as quiz question. Okay, and you will be asked to find out certain unknowns. All right, fine. Now let me see whether I can solve few problems from other circuits. Okay, fine. So this particular problem is based on transformer-based push-pull power amplifier circuit. Okay, it had come for 8 marks. All right. So take down a Class B push-pull amplifier drives a load of 16 ohm. A Class B push-pull amplifier drives a load of 16 ohm. VCC is equal to 25 volts. Number of turns in primary is 200. Number of turns in secondary is 90. Okay. Calculate maximum power output. Calculate maximum power output, say P naught AC maximum. Efficiency. And maximum power dissipation per transistor. So in short, let me write. So maximum power dissipation per transistor. So let me write it as PD max per transistor. Okay. So this is the problem. Okay. Fine. So first let us find out the transformation ratio. So solution, let me write. Okay. First you find out K. K is N2 by N1. So what is N2? 90. And what is N1? 200. So that ratio gives transformation ratio of 0.45. So obviously it's a step down transformer as expected. Okay. Once you know this transformation ratio, what you do is you find load resistance refer to primary. So load resistance refer to primary. Let's take it as RL dash. So RL dash is nothing but RL by K square. Okay, so that's 16 divided by 0.45 square. So RL dash, you will get it as 79.012 ohm. ohm. Okay. Now I can, go ahead with the further part of the problem. So firstly, we need to find out P naught AC, right? Maximum AC output. So P naught AC maximum condition is VCC is equal to VM is equal to 25 volts. Okay. So therefore, P naught AC maximum is equal to half Vm square by RL dash, okay, where Vm is equal to VCC, right? Because we are considering the maximum power. So you would get P naught AC maximum as half into Vm. Vm is 25 square divided by RL dash. So RL dash is 79.012. Okay, let me just cross check. 3.955. So the maximum power output is 3.955 watts. All right. Okay, done. Next, we need to find out percentage efficiency. So percentage efficiency is P naught AC divided by PDC. Okay, so over here, P naught AC is nothing but AC max. That's because there's no, VM value they haven't given. So you must consider that the maximum AC output itself is the usual AC output. Okay, so P naught AC maximum we have already calculated. Okay, in the previous step. So what you need to do is you need to calculate PDC. Okay, so PDC is VCC into 2Im by 5. Right, VDC into 2Im by 5. Now, what is this Im? So Im is Vm divided by RL dash. Okay. Once again, there is no Vm value given in the problem, but let us assume that the circuit is operating at the maximum efficiency condition. So at maximum efficiency, Vm can be taken as VCC divided by RL dash. Let me write on the side that Vm is equal to VCC for maximum efficiency condition. All right. So I get Im is equal to VCC. What is VCC? 25 divided by 79.012. So that is 0.3164. Okay, so that is my Im. So therefore, so I can substitute this Im in my PDC expression. So that's 25 into 2 into Im. Im is 0.3164 divided by 5. That's 5.036. Okay, so therefore percentage efficiency is equal to P naught AC. So P naught AC is 3.955 divided by PDC 5.036 into 100, and that is 78.5%. Okay, so that's your percentage efficiency. So we have found the second part as well. And finally, you need to find out PD max, right? That is maximum power dissipation, with which you will be able to find power dissipation per transistor. Okay. So for PD max, we have Vm is equal to 2 by pi VCC. Okay. So Vm is equal to 2 by pi VCC. That's 2 by pi into 25. So basically it is 50 divided by pi. That's 15.915 volts. So that's your Vm. Okay. So therefore, PDC max, I'm so sorry, it's not PDC max, it is PD max. Okay, so PD max is equal to 2 by pi square into VCC square divided by RL dash. Right, this formula in problem number 2, I think I have solved. Okay, so that's 2 by pi square into 25 square divided by 79 point, how much? 012, right? So PD max is equal to 2 into 25 square divided by pi square so that's 1.603. So maximum participation is 1.603. Therefore, PD max per transistor is equal to 1.603 divided by 2, and that is 0.801 watts. Okay. So that is your problem number 4. Okay, very simple problems. Conceptually, you need to move forward. Okay. Last problem let me solve for the day. If at all, if I find any. Okay, yeah, I mean, that's it. That's more than sufficient. Okay, so few self-learning topics. Okay, so first self-learning topic could be differences between transformer coupled class B and complementary symmetry class B. Okay, differences between transformer coupled class B and complementary symmetry class B. And the second topic will be merits or advantages, merits and demerits. Demerits is nothing but disadvantages. Merits and demerits of class B power amplifier. Okay. So when you say merits and demerits, you have to talk about both the types. Okay, both the types. See, I can tell about merits and demerits, but you can also go back and you can do some kind of survey also. Okay, if you look at transformer coupled class B power amplifier, the merits could be something like higher efficiency and better impedance matching due to the presence of transformer. Okay, so these are the two major advantages of class B transformer coupled power amplifier. On the other hand, the disadvantages could be, due to the presence of two transformers, one at the input side and one at the output side, the overall weight of the power amplifier circuit increases. So the circuit becomes less compact and more bulky, and the cost of the circuit will also be very high owing to the presence of the transformers. Okay, so the cost factor is another disadvantage, and the third major disadvantage could be the poor frequency response due to the presence of inductor. Okay, so these are the merits and demerits of class B transformer coupled push-pull power amplifier. On the other hand, if I were to consider class B complementary symmetry type power amplifier circuit, merits could be lighter weight, lesser number of components, and cost effective. Okay, and better frequency response. Okay, and in the demerits, it suffers from crossover distortion. Okay, so I have already discussed. Probably you can put it in better sentence. Okay, so that is about your class B power amplifier circuit. Okay, now there's a small portion left out. Okay, and that small portion is called as distortion in power amplifier circuit. Okay, distortions in power amplifier circuits. Okay, now actually in the syllabus they haven't mentioned distortion in power amplifier circuits. I do not know whether it is a printing mistake or not, but for the past in the past two external valuation which I have corrected, questions have been asked from distortion in power amplifier circuits, and VTU has never told that these questions are from out of the syllabus. So I assume that distortion in power amplifier circuits is not included in the syllabus due to the printing mistake. That's the reason I find it very important to discuss about the distortion in power amplifier circuits. Okay, which I'll be taking it up in the next class. So next class, let us just discuss about distortions in power amplifier circuits. All right.